Suppose we have a sorted list of n distinct numbers and we want to determine whether some target number is in the list. So the rules are simple. We can expect one position in the list at a time, and each inspection reveals the number at that position. And each inspection is going to cost 1. You can think of it as costing like $1. So our goal is to find an efficient strategy, or more precisely, want to minimize the total cost in the worst case. So one possible strategy could be to start at the beginning. So here, imagine you have your n numbers here, and you're searching whether one of these is the number 7. So you want to find number 7 here. You could obviously start at the beginning, check what number this is. If it's not 7, you continue until you make yourself all the way to the end. Now, of course, if you do that, in the worst case, you're going to have to look at all the n entries. And so the question is whether we can do better than that. And one of the key facts here is that this list is sorted so that we know that this number is smaller than this one, is smaller than this one, is smaller than this one. So can we use the fact that the list is sorted to get like a much better performance than, let's say, worst case, having to look at everything, right? And so binary search uses exactly this extra information. The list is sorted. And the strategy with binary search is to inspect the middle element first, right? So if you go back here, ask about what's the value in the middle. What is the number in the middle? The idea being that now, if you know the number in the middle, let's say is 10, then you know that 7 is less than 10, then it's going to have to be on the left side. And if this was like a 5, then 7 is larger than 5, it'll have to appear on the right side, right? And so the idea is you inspect that middle element first. If the middle element is equal to the target, then of course you're done. And if it is not equal to the target, then the sorted order tells us where the target could still be, right? So like we said, if the target is smaller than the middle element, then it cannot appear in the right half of the list. So we discard that right half. And then if the target is larger than the middle element, then it cannot appear in the left half. So we discard the left half. Then we repeat the same process on the remaining half. So you can notice how this is essentially breaking up the search in a list of size n into checking the middle and then doing a search on a list of size n over 2, right? So each step costs 1 inspection, but each step also cuts the problem size roughly in half. And so that's the key idea behind binary search. So let's analyze the cost of binary search. So let T of n be the worst case number of inspections needed for a list, for a sorted list of size n. And so again, at the first step, binary search inspects. So if we're going to try to get a formula here. So in the first step, what we do is we check the middle element. And so that has a cost of 1. And then the idea is that you then have your list of about size half. And so you just need to do the same algorithm again, the binary search, on a list of around half the size. And so this gives you a recursive formula where it depends, the current state depends on like half the size of the problem, right? And so you continue to do that again and again and again, right? And so this is our recursive formula. And of course, there's an initial condition. If you have a list of size 1, of course, you just need to check that entry and you'll get the answer. So that's how you solve that one. And so with these two, you can sort of solve for every problem. Here, for simplicity, I'm assuming that n is some power of 2. So here, let's say assume n is a power of 2. Why? Because so that we can always do this n over 2. Now, if it's not a power of 2, you can sort of find the closest power of 2 and you divide that amount, and so things are going to be different by a constant. And for now we're just wanting to do better than, for example, like a linear search, something that grows like n. So for now, let's assume that n is a power of 2, and the non-powers of 2, it's just going to add some extra constant to whatever you're doing. So okay, so let's solve this recurrence here. So one way we can solve this is by expanding. And so the idea there is that if we start with t of n equal to t of n over 2 plus 1, you can write this out. So we know that t of n over 2 is going to be t of n over 4 plus 1. And then we know, and let's just write this one completely out. So this is just going to be t of n over 4 plus 2. Now you can replace this t of n over 4, and so this is going to give you t of n over 8 plus 1 plus 2. So you get t of n over 8 plus 3. And if you continue to do this, you should get something like t of n equal to t of n over 2 to the k plus k. So if you do this k amount of times, right? And the idea is that if n is a power of 2, you'll eventually do this until you get t of 1. And we know that t of 1 is equal to 1. And so if you do this enough times until n 2 to the k is equal to 1, so this implies that n is equal to 2 to the power of k, which implies that k is equal to log n, here log n base 2. And now if you replace this here, you'll get the solution that just t of n is going to be equal to log n base 2 plus 1, right? So think of it, let's see this again. So I'm just rewriting this. And you do this until this is equal to 1, right? So let's say you do this until this is equal to 1. When this is equal to 1, you get t of 1 plus k. But we know that t of 1 is 1 and k is log n. So base 2. And so that's how you get this formula here.